In today's video, we want to dive into thin layer chromatography. So we are going to see the comparison between thin layer chromatography versus high performance thin layer chromatography. And as we start, if it is your first time, please subscribe. Remember to like the video and share so that we may continue to grow with you for betterment of serving society. So with thin layer, as its name, thin layer, it means the stationary phase is going to be made up of either glass or a plastic plate which is thin, which is coated with a thin layer of either silica, alumina, or cellulose. That's why we call it a thin layer. And the use, this one is being applied in pharmaceuticals, in clinical labs for separation. We're using it to separate, to identify, and semi-quantitatively, because this one does not give a quantitative, but it can accept the high performance which will be able to quantify. So we can also say also to quantify non-volatile. Here we are looking at non-volatile substances. So this is the first thing to note, that we are using thin layer chromatography to separate and identify non-volatile compounds. These are compounds which do not easily vaporize at room temperature and even at high temperatures. So those are the substances we are able to separate or identify in a sample mixture. And under the principle, we are going to see that we have still phases whereby we shall deal with the stationary phase, then we have the mobile phase and the chamber, the TLC chamber. And the stationary phase, as its name says, is made up of a thin layer, and this thin layer is either made up of glass, a glass plate, or a plastic plate. And these two are coated with stationary solid substances such as silica, which is the most commonly used, is silica gel. It can be coated with a small layer of alumina, which is a basic substance, or we can use cellulose. So these are thin layer of a solid phase. So this stationary phase is solid in nature. It is solid in nature, so it is going to work under the principle of adsorption, since it is a solid in nature. And don't forget that the most commonly used is silica gel. And the solid phase should be polar. So we are using solid phase which is polar. The silica gel, the alumina, and the cellulose, they are all polar, with the size of these gels, it ranges between 2 to 25, between 2 to 25 millimeters, which is going to be different from high performance, which deals with between 2 to 10 millimeters, or sometimes can go up to 5. That is the difference. And this stationary phase is always vertical. It is always the setup is always set up in vertical position. So meaning the mobile phase will be able to be moving by capillarity action. So the movement is by capillarity, which is going to be different from high performance thin layer chromatography, which the stationary phase is horizontal. Here the stationary phase is horizontal. So the solvent or the mobile phase is able to move faster compared to the thin layer, the ordinary one, whereby the stationary phase is vertical and the movement of the solvent is by capillarity. So this one makes HPTLC very effective. This one uses semi-quantitative methods of visualizing, for example, UV light, iodine stain, potassium permanganate, but we shall see HPTLC using quantifying using densitometry or densiometer. It is able to quantify and give figures, which is different from this, which is semi-quantitative. So that's why currently we are employing HPTLC compared to the ordinary thin layer chromatography. So after understanding the solid phase, then what about the mobile phase? The mobile phase is made up of also a solvent or solvent mixture, and this solvent, its polarity is going to depend on the sample being used, whereby some are less polar, others are more polar. Like hexane, ethyl acetate, those ones are less polar, whereas the ones which are more polar include methane and chloromethane. So they are also polar. So examples we can give under mobile solvents is solvents like hexane, methane, pentane. Examples like dichloromethane, all these are used. Diethyl acetate, diethyl ether is also used. Then ethyl acetate. And in reverse thin layer, we can also use water methanol mixture. So all these are mobile phase. And the importance of the mobile phase is to move the sample mixture, whereby we are going to see it under the procedure. Then we have the chamber. This chamber must have a lid, and its importance is to keep the internal environment constant. So it is to keep the humidity inside of the chamber so that it does not differ to affect our results. Then lastly, under the components, what we shall also need is the sample mixture. And this sample mixture, in the beginning, as we said, the sample we are separating must be non-volatile. And the separation is going to depend on the affinity. So these samples are going to be separated depending on their affinity to the stationary phase. Those which have much love or affinity for the stationary phase will interact more and will be able to migrate slowly compared to those with less affinity. Those with less affinity will migrate faster and will be able to be separated from those which are have more affinity to those which have less affinity. So in summary, the principle is that when a sample mixture which contains non-volatile substance to be separated is put on a stationary phase made up of glass or plastic coated with silica gel, is placed into a thin layer chamber containing the solvent, and then the lid is applied. We are going to see that the inks which were applied are going to migrate depending on their affinity or interaction with the stationary phase. Those which have more interaction with the stationary phase will move slowly compared to those which have less affinity to the stationary phase. And we shall be able to determine them by calculating what we call retention factor. Retention factor, as we are going to see the formula. So that is the simple principle we can state. Afterwards, we are able to draw it and visualize by using different methods like UV light fluorescent. We stain with the fluorescent dye and we examine using UV light, or we can use iodine, potassium permanganate, depending on the non-volatile substance being separated. So let us look at the procedure. What is the procedure? So the procedure for this is that we are going to obtain a thin plate or a plastic plate or glass plate coated with either silica or alumina or cellulose. But as we said, more we use the silica. So this one is coated with silica. For me, I'm choosing to use silica gel. So after obtaining it, using a pencil, we are going to draw a line across 1 centimeter from the bottom. This line should be 1 centimeter from the bottom. After drawing this line, we are going to come and apply different spots at equal distance. So we can come and apply different spots, but with equal distance in between them. So I have applied this spot A, B, and C. These are different substances, non-volatile substances, which I'm interested to separate and identify. So after applying them on the line drawn by the pencil, we are going to come and place this solvent with this stationary phase coated with the silica and the sample mixture to be separated. We are going to come and we place it into the thin layer chamber. This thin layer chamber is containing the solvent, which is going to act as the mobile phase. So after placing it, we are going to see, we place it, but we make sure the line is at least 0.1 centimeter above the solvent. So we come and place this in the mobile phase, but the line of application should be at least 0.5 centimeter from the solvent. So this was the line which was put, and these are my spots or dyes A, B, and C. So after placing it in TLC chamber, we apply the lid. We come and apply the lid to keep the humidity or the vapor within, so that the environment remains the same and to prevent it from drying. That's why we put a lid. So we come and put a lid and we intubate for a time specified by the manufacturer. So during intubation, we are going to see these dyes are going to start migrating together with the solvent in the stationary phase. So if this is my thin layer, during intubation, remember the ink or the dyes containing the compounds to be separated was here, a little bit above the solvent. So we are going to see these spots migrating depending on their affinity to the stationary phase. So if substance A, B, C, so they are going to start migrating. You'll find this one has migrated up to this point. You find this one was able to migrate up to this point, and the C was able to migrate up to this point. So these these spots are able to migrate at different height or length depending on their interaction with the stationary phase, which is silica gel. So after this, so the solvent was also able to move. What enables them to move is the solvent, because the solvent is going to be absorbed by capillarity with this stationary phase. So it is absorbed, and maybe let me say this is the solvent front. Then these are the spots we put. So this one is what we are calling the solvent front. So after intubation, these different spots or dyes are able to be separated depending on their interaction with the solvent, with the stationary phase. We are able to remove it and dry it. So when we dry it, this was our solvent phase. So our solvent was able to move. After drying, if it was, we can stain it with fluorescence, and we visualize using UV light, as we are going to see different visualization method. So according to our separation, we see spot A, which was here, has been able to move up to this point. Spot B was able to move up to this point. Then spot C has moved up to this point. This is the way they have managed to migrate depending on their affinities with the stationary phase, which is silica gel. So after this, what we do, how do we determine? We can determine this by calculating the retention factor. Let me use an example. Maybe A was able to move 2 centimeters. B was able to move, on measuring with the ruler, it was 4 centimeters. Then C was able to move maybe 8 centimeters. And then the solvent front was 10 centimeters. Because we normally stop when the solvent stops moving, and we are able to calculate the movement, the height of their movement or length. So after getting this, I am able to calculate the retention factor of each substance, whereby retention factor is calculated by the length moved by the substance or compound divided by the length or height moved by the solvent. That is how we are able to calculate. So in our example here, for example, for substance A, the retention factor of A is equal to the distance migrated by substance A, which is 2 centimeters, divided by the solvent front, which is 10 centimeters. Then the retention factor of B is equal to 4 centimeters, which have been moved, divided by the solvent front. Then for retention factor of C is equal to, it has moved 8 divided by 10 centimeters. Here we are getting 0.2, here we are getting 0.4, here we are getting 0.8. And for a better thin layer chromatography, the retention factor should be between 0.2 to 0.8. That is how we can able. And the retention factor has no units because it is a ratio. So these are the answers how we are able to determine their retention factor. But how do we visualize them? These are the different methods, because before we start to measure the length of their movement, we have to first stain for better visualization. And how do we visualize? We are using methods like staining them with fluorescence dye, and we visualize using UV light. We are able to see different spots of the samples we applied. Another method, which is number 2, we can use iodine. And this iodine, it will target majorly carbohydrates like starch, and it is able to color them brown color, blue-black, to give it blue-black color, hence able to be visualized. Number 3, we can use potassium permanganate solution, which this one targets for sugars, presence of sugars like glucose, and it can also be visualized. Another substance we can use is ninhydrin, and this ninhydrin targets for the amine groups in samples which contain substances like amino acids can be separated by staining with ninhydrin solution. So these are some of visualizing methods, though we are saying these ones are semi-quantitative or even qualitative. But with the involvement of high-performance thin layer, we are currently using densitometer to quantify and get our recorder in form of a graph, and we are able to quantify by looking at the area under the peak. That is what we can tell you. So this is what we can discuss with you under thin layer, and this is the same as paper chromatography. The difference is in paper chromatography, you will stop on the retention factor, and we are not able to quantify using these methods. That is the challenge with paper chromatography. But thin layer and paper chromatography, they use the same principle. Maybe the detection is the one that differs, whereby in thin layer we are able to stain with fluorescence and visualize using UV light, which cannot be used under paper chromatography. So this is what we can show you, and we have seen how we are able to determine the retention factor. Lastly is application. Where can this thin layer chromatography be applied? So it is being applied both in pharmaceutical industries, can be applied in food industry, in cosmetic industries, and also in clinical labs. And all this, we are applying it, for example, in pharmaceutical chemistry. It can be applied to determine or identify different dyes or chemicals in formulation of drugs. It can be used to determine presence of impurities, to identify presence of certain impurities. So meaning we are able to remove them after identifying them. And another thing we can do is also in pharmaceutical industries, we can use it also to identify, apart from seeing the presence of impurities, we can also be able to quantify them. For example, using high performance thin layer chromatography, can be able to quantify. Still in the food industry is to look for presence of toxins in food products. In cosmetics, also to identify chemicals used, different chemicals in products. We can use it. Then in clinical labs, we can also use it to identify presence of toxins, stroke, drug of abuse, qualitatively in the body by using thin layer chromatography. So this is what we discuss with you. Please remember, the stationary phase is polar, and a smaller layer of silica gel, which is commonly used or alumina or cellulose, is coated on the glass, and it is always in a vertical position, which is different from high performance, which is in a horizontal position, and this one enables faster movement. That is the advantage of high performance. Another advantage is that this one, the stationary phase has big size, whereas this one has smaller size, which makes high performance thin layer very effective. That is why we prefer high performance thin chromatography. We have seen the type of mobile solvent used and that's why we use it for separating non-volatile substances. We have gone ahead to look at the procedure, how it is done, and how to calculate the retention factor by looking at the distance moved by substance divided by distance moved by the solvent, which is the mobile phase. And we are able to record them. And we have used this example. We have gone ahead to look at different visualization methods, whereby we have UV light using iodine vapor, potassium permanganate solution, and anhydride, and others. And we have ended by looking at the application. Thank you so much for learning with us at Medical Sciences. May the good Lord bless you. Please remember to like and share to many others. Thank you so much.